And you know what? See, part of the problem now is all of the money for climate change research is now going towards anthropogenic climate change, which means what? Humans, right? Do humans cause climate change? Of course we do. Do humans have an influence on climate? Of course we do. Have we increased the amount of CO2 in the atmosphere? I think it's pretty clear we have. Does the amount of CO2 in the atmosphere fluctuate naturally? Yes, it does. Have there been climate perturbations, climate disruptions that go far, far, far beyond anything we've seen in the last 100 or 200 years? Most definitely yes. And this is what I'm trying to introduce you to here now, is that because right now 99.99% of humanity on planet Earth is utterly oblivious to the true dynamic history of this planet, or the true dynamic history of human population and culture and civilization on this planet during the last couple of 100,000 years. Now, what's all this have to do with the Holy Grail? Well, it has everything to do with the Holy Grail. Here's my take on what the Holy Grail is. The Holy Grail is basically an encoding of the technology whereby human beings can accelerate the regeneration of the planet in the aftermath of a catastrophe. So you're familiar with the Finger Lakes?
Yeah.
See the Finger Lakes? Why they're called Finger Lakes? There's several things that are really interesting about the Finger Lakes that have relevance to our discussion. One is this. Each one has an axis, right? And if you follow that axis, what do you see happening here? There's an epicenter right there. How many people have noticed that before? But it's very significant in understanding how those Finger Lakes formed and what they actually are. Because you know, some of those Finger Lakes, the two biggest ones, they're like 800 feet, the bottom of them is like 800 feet below sea level. Below sea level. And then they're about filled up halfway with sediment. And it was always assumed that the Finger Lakes had formed over, you know, many tens of thousands, maybe even hundreds of thousands of years. Probably gouged out by a succession of glacial ages, because all of this area was under ice during the glacial age, right? Well then, about 10 years ago, a couple of teams started extracting cores from the bottom of these lakes. And what they discovered was really interesting. And it was this, that the material, there's bedrock troughs. They're like 1,500 feet deep. But then they're half filled or more with sediment. So the assumption was that the sediment was probably something that accumulated over long, long periods of time. Well, they took core samples from the bottom of the lake through the sediment right down to the bedrock, right? And then they started radiocarbon dating organic material that they found in there, and all of the radiocarbon dating dates of the material was coming up at less than 14,000 years. Let's think about what the implications of that are. If all of the dating on this material was less than 14,000 years, what's that implying? George?
14,000 years ago.
What?
After the Ice Age.
But they were formed 14,000 years ago.
Post 14,000 years. Post 14,000 years. Now, so then you have to ask the next question, is you've got these deep, basically scours, like they're like scars in effect. They're deep gouges right down into the bedrock. They're then filled up with material. The assumption was always, before these studies, that these things were going back tens of thousands and 50,000 or more years, multiple ice ages come and gone. glaciers scouring them out. But there's another important clue here. It's this area right up in here. And let's just see if Google Earth will actually, if we can see it on Google Earth. Look at this landscape there that's between the north end of the Finger Lakes and the south shore of Lake Ontario. Look at these things. What are they?
It looks like some kind of battle was there.
Well, you know what? In a way, there was kind of a battle that went on there. You see, there's the lake up there. And you can see that they start right along the lake. In fact, it looks like they're actually truncated by the edge of the lake. And then...
And they're also pointing to the same epicenter, aren't they?
Yes, they are. Very good observation. They're pointing to the same epicenter. These are what are called drumlins. And what is a drumlin? Well, a drumlin is something that's always been associated with glaciers, because everywhere they've been found in the world are places where there had been huge ice sheets. So the assumption is that these things had been formed somehow by the glaciers moving across the landscape, gliding, but glaciers don't glide, they grind across the landscape. And we can't really see on here too good, but each one of these things in effect, let's see, maybe we can even zoom in a little further. And you can get a sense of the shape of these things. They're like inverted boat hulls. They're like inverted canoe hulls in a sense. They're pointed, they're tapered, they're round, very much the same shape. They're very aerodynamically or hydrodynamically shaped. And it has been proposed that drumlins, and I'm showing you a famous drumlin field here. This is the western New York drumlin field that's between the lake and the Finger Lakes, between Lake Ontario and the Finger Lakes. So you've got thousands of them there. Well, they were almost certainly formed by water, not ice. And they would have been formed by water moving under the ice sheet under tremendous pressure. Now, you have to put this together. What we're seeing here is that we have a radiant epicenter, we have this drumlin field, then we have the Finger Lakes spreading out from that same epicenter, right? Now, how could you form the Finger Lakes? What I'm going to do is I'm going to go back to Google Earth, and I'm going to zoom out, and I'm going to go across the United States. I'm going to introduce you to a feature called Grand Coulee.
Is that the Scablands?
All right. See this thing right here? You notice how it's an elongated lake? It's a bedrock trough. Very similar in scale, in depth, in width, in length to one of the major Finger Lakes of New York. Okay? Now, this is part of a coulee. It's called a Grand Coulee. You ever heard of Grand Coulee Dam?
Yeah.
Grand Coulee Dam is the largest reinforced concrete structure in North America. And for a long time, it was the most massive in the world. Not the highest, but the most massive. It's over a mile wide, and it's about 400 feet, roughly, in height. Yeah. And it's right here. This is the Columbia River, comes this way. And right there is the dam, which forms Lake Roosevelt, which backs way up here, almost to the Canadian border. Grand Coulee is this feature right here, which gives its name to the dam that's at its north end. Now, what I'm suggesting is that the forces that created the Finger Lakes of New York are very similar to the forces that created Grand Coulee. So how was Grand Coulee created? George, you've had a little bit of exposure to this.
Maybe
what?
An impact of some sort? Or maybe, I don't know.
Not exactly. Maybe. Okay, how did I say that drumlins were formed?
By massive water pressure moving under the
Water,
ice.
water. Water is the key agency here. And the reason I'm getting into this is because water is so critically important to understanding the whole Grail mythos, right?
Okay.
Remember the first card I showed you, showing the water pouring out of the cup?
Right.
And I'm suggesting that on the scientific interpretation, what that represents is water flowing out of a basin into the hydrosphere. And what is the hydrosphere?
All the water on the earth.
All the water on the earth. It's the oceans, it's the creeks and the rivers, it's the groundwater. It's even the rainfall. Rainfall is part of the hydrological cycle. But the hydrosphere is the sum total of all of the water on earth in whatever form. Now, ice sometimes is referred to as the cryosphere, like as in cryogenics. But ice can be part of the hydrosphere as well. But basically the hydrosphere is all of the water of the earth. Okay, so let's see here. Let's look at this. Here is Grand Coulee. This is what's known as Upper Grand Coulee, and this is Lower Grand Coulee. Now I'm going to show you something here. We're going to zoom in on this zone that's between the two Upper and Lower Coulees.
And that straight line there, that's not a dam?
This straight line is a dam. It's Banks Lake Dam.
Huh.
Yeah. But what I want you to look at is what's below the dam. I want you to look at this texture. And then I want you to look at this interesting complex of features here. What is that? What we are seeing here is giant abandoned cataracts. And what is a cataract? Tim, you've been to Niagara Falls undoubtedly, right? You remember Horseshoe Falls?
Yeah.
This is like Horseshoe Falls. These are cataracts. They're abandoned cataracts. Cataracts are formed by high velocity, high pressure floods sweeping across the landscape with such force and intensity that they're just plucking the bedrock as they go. And that's what we're looking at here. We're looking at a hydrodynamically created landscape. And if you look at this, what you're going to see here is that the Coulee itself is, you'll see here, if we zoom out a little bit, you can see that the Coulee, notice the Coulee is a giant channel. It's basically about a mile wide, varies about 800 to 1,000 feet deep. It was estimated that the Coulee might have taken anywhere from 3 days to 2 weeks to be cut. Now, normally what most of us were taught was that change that happens on the earth happens very slowly, one grain of sand or one drop of water at a time, and it's very uniform, very gradualistic. But all along there have been these maverick geologists that have been saying, well, that may be true most of the time, but not all of the time. Sometimes the pace of change gets accelerated orders of magnitude above and beyond the normal rates that we're familiar with in modern times. We're seeing here a feature that was a consequence of one of these episodes, one of these non-linear episodes. If we think of linear change being the change that is gradualistic, what's basically we've experienced, what humankind has experienced in historical times, what we're looking at here is something that is, again, orders of magnitude greater. In fact, the estimate is that the water flow that passed through here and ultimately, which was channeled along this here, and then right here it began to spread out. As it cleared the channel and began to spread out. The amount of water estimated to have been involved in this flow here that came down like this, spread out here, is about 300 to 350 million cubic feet per second. Now, if you took every single creek and river and stream on Earth every drop of flowing water, and I'm talking about every major river in North America, Mississippi, Columbia, the Chattahoochee, right? The Rio Grande. If you took every river in Canada, the Yukon, the Mackenzie, if you took every river in Europe, in British Isles, from the Thames, you took the Hudson River, the Amazon, the Nile, the Yangtze, the Yellow River, every single river on Earth, and put all of those flows together, it would be less than 1/10 of this flow right here. That's a pretty interesting phenomenon. And what caused such a flood as that? See, this is the question. And for years, there was a lone geologist by the name of J. Harlan Bretz who was studying this landscape and landscapes nearby. When I zoom out here, so you can see the bigger picture, and this is where it's really cool, is because we are in this position now where we can see stuff that could once only be seen by months and months of exploration on the ground. Look at this right here. Look at this. Look at this over here. Now, this is southeastern Washington. And all of this speckled stuff here is agricultural, being cultivated because it's very fertile. And all of this up in here is what's called loess topsoil. And I think we talked about that in lecture 1 a little bit. Underneath this loess topsoil, which is in some places a couple of 100 feet deep or thick, is black basalt, lava rock. And that's what this stuff is, this dark that we're seeing here. And this is what has been known as the channeled Scablands. And we'll just zoom in a little here so you can see it clearer. You had huge floods that came down like this, washing over the landscape, stripping away the 200 feet of loess topsoil and exposing the dark bedrock below. Now, here's Grand Coulee, so you had a flow coming down this way, and I said it was about 300 to 350 million cubic feet per second. Now, in 1993, some of you may remember, there was a big flood in the Mississippi River, right? It was the second biggest flood in the Mississippi River of the 20th century. I think the biggest one was either 23 or 27. And it caused, at that time in 1993, it was the most economically expensive natural disaster in American history. I think it's been superseded by several events since then. But yeah, in 1993, and it was the second largest peak discharge on the Mississippi River ever measured. Now, the average of the Mississippi River is about 200,000 cubic feet per second as you get down to New Orleans. At the peak of the flood there, I think between New Orleans and St. Louis, they measured it at about 1 million cubic feet per second, about 1 million. I said that this flow was about 300 million. So basically, think about that. That would be about the largest flood discharge ever measured on the Mississippi River times 300. Or the normal flow of the Mississippi River by 1,000 to 1,200 to 1,500 times. It's that much water flowing just in this one, see? Over here, you had about the same amount of water. And over here, again, you had about the same amount of water. Somewhere roughly between 250 and 400 million cubic feet per second. Now,
For how long did this happen?
for how long? Most likely a matter of a few days to a few weeks, somewhere in that span of time. So now, already you can see, if we start adding these up, look at what we're approaching 1 billion cubic feet per second. If we go over here, notice this arc-like feature right here. There was a lobe of ice that came down here, part of the great ice sheet that covered Canada and the Canadian Rockies. Was called the Cordilleran ice sheet. A tongue of the Cordilleran ice sheet came down and it stopped right here. And it left this very defined line right here. And at the terminus of an ice sheet, the material that is accumulated there is called moraine. Moraine is like, it's like almost the material that's been bulldozed ahead of the glacier, and it mounds up. And oftentimes, if the snout of the glacier is rounded, the moraine will basically be more rounded. The stuff that composes moraine is called till, and it's the material that's just ground up by the glacier. It's boulders, it's gravel, rocks, sand, organic material, whatever happens to be in the way of the glacier. It gets ground up and becomes till. At the end of the glacier, you have what's called a terminal moraine, right? Because it's at the snout or end of the glacier, and it's composed of till. Sometimes along the edge of a glacier, you'll have what's called a lateral moraine, because it's on the sides of the glacier. And if two glaciers flow together, each with their lateral moraine, and those two glaciers come together and form one glacier, you then have medial moraine. So you guys are learning some serious geological terminology here. You can really impress your friends with it, which is the main reason why we learn terminology like that, right? You're out driving with your friends. Oh, I believe that. Isn't that some medial moraine over there? Okay, but here's what's interesting. We can see right where the end of this glacier ended, right here. And then we could trace that glacier right back up into the Canadian Rockies, filling mountain valleys 3, 4, 5,000 feet thick, right? But coming off the snout of this glacier terminus right here, and oh, by the way, you see, if you're actually traveling, and when we get to this, I'll be showing you slides from the ground level, so you can now get the perspective, the altered perspective between this view, which is essentially the satellite view, and then the ground level. So what happens is this area here is very bouldery and rocky. It's not suitable for farming. But as soon as you get south of where the glacier was, you see these squares? Those are fields where they're being cultivated, see? So now you've got this loess topsoil, which interestingly is extremely fertile stuff. Thing is, though, southeastern Washington only gets about 15 inches of rainfall per year. So the idea is that there's not a lot of moisture there, which is kind of ironic because you've got some of the richest, most fertile topsoil in the world there. But if you add water to it, it's like it comes alive. And so some of the best apples that we eat come from this area out here. It grows really great. There's orchards all over the place. Most of these are going to be, I think, orchards. In any case, look at this feature right here. You know what that is? That's a scar. It's a coulee, just like we call this a coulee. I don't know the origin of the term coulee, but it applies. It's different than a canyon, because a canyon will usually or invariably have a river flowing in the bottom of it. Coulees do not. Either there's no water flowing in them, or the water is so insignificant that it's clear that the amount of water flowing into coulee has no relationship to the scale and scope of the coulee itself. Now, there is water here, but see that up until the Bureau of Reclamation project back in the 30s and 40s, when they built Grand Coulee Dam and Banks Dam, there was no water here, right? What they did was they created this reservoir, and Grand Coulee is about 800 feet higher than the Columbia River. They've created this huge hydroelectric dam right here, Grand Coulee Dam, and they built this dam, and now they're using this as a reservoir, and there are aqueducts feeding off of this reservoir out over the loess landscape to bring water. And that's how they're able to conduct their agricultures, by bringing the water to this fertile loess topsoil. The loess itself is very interesting, unusual stuff. And we'll probably come back to this idea of loess and what actually it is. It's spelled L-O-E-S-S, but it rhymes with bus. If you're interested in doing any extracurricular work, you can always look it up and read some background on it. So we've got this thing coming off of here, and it's called Moses Coulee. This is called Grand Coulee, this is Moses Coulee. And let's just take a closer look at Moses Coulee. Now what we're seeing here is where lower Moses Coulee comes down and meets the Columbia River Gorge. And it comes to a point right here. And notice there's farms and stuff here. There's this big flat area. It actually extends down off the screen somewhat. You can see it extends, in fact, all the way down here, like this. Now, how was Moses Coulee created? Well, basically the same way as Grand Coulee. It's a gigantic flood channel. And again, the flow of Moses Coulee was roughly the same as the flow of Grand Coulee. So now we're talking Grand Coulee, Moses Coulee, the two Scabland tracks that I showed you, and we're looking at well over 1 billion cubic feet of water flowing over this landscape. What was the source of so much water? Well, what was just to the north of this area? We saw right here at the top end of Moses Coulee, in fact, we're following the Coulee right up, and we're actually seeing a huge scar in the landscape. Now, this scar, to a geologist that has studied catastrophic episodes in the history of the Earth, this scar is as obvious in what it's conveying in terms of the violence of the events as if you, for example, saw somebody who had been in a horrible car wreck or a war veteran that had been horribly scarred and burned, and you looked at them and could immediately tell this person has been through something very traumatic, right? With the untrained eye, most people would look at this and not understand what they're really seeing here. To the trained eye, though, what we're seeing here is evidence for these tremendous violent events. Now, what the mystery here is we have to come up with some way of providing the source for so much water in excess of 1 billion cubic feet per second, a minimum of a bit. When you look at, if each one of those was 300 to 350 million, and there was the two Scabland tracts, one of them was called the Cheney-Palouse, the one was called Telford, then Grand Coulee, then Moses Coulee, the total flows of all those four may have been between 1 billion and 1.5 billion cubic feet per second. So remember I said that 300 million cubic feet per second is more than 10 times the combined flow of all water on Earth flowing at once. Now we're talking about perhaps in excess of 1 billion cubic feet per second. Humanity has not experienced anything remotely like this in historical times. But it's interesting that when we begin to ponder this kind of stuff and we begin to realize that these kind of events are very real in Earth history. And not only are they real, but they're very recent. We're looking at events here that only happened between, say, 11 and 13, maybe 14,000 years ago. In fact, the age of these things appears to be identical to the age of the Finger Lakes in New York. Now, what I'm suggesting here is that when you look at the Finger Lakes and their erosional patterns, and you look at the drumlin fields, and then you realize that those drumlin fields, the north end of the Finger Lakes, marked the southern edge of the eastern ice sheet. Okay, so we've got a couple of factors that we have to kind of integrate here. We've got massive amounts of ice covering Canada, and now what I'm showing you is evidence that there was some extreme melting of that ice. Because that's where you're going to get these hundreds of millions of cubic feet per second pouring off the ice. There's no other source for it. And in fact, we can see in terms of the distribution of these features and the geomorphology that they're directly connected to the ice sheets themselves. So now we're faced with a conundrum that geologists and climatologists first encountered in the early 70s, which they call the energy paradox. Now, the assumption has always been, up until the 70s, that the disappearance of the glacial ice maybe took 50,000 years or longer. And that was based upon estimates of recession time of modern glaciers. We've been watching modern glaciers recede since the mid-19th century, early to mid-19th century. The recession of glaciers that's been going on in the last 2 or 3 decades has actually been going on for 150 to 200 years, since the end of the Little Ice Age. Now, during the Little Ice Age, there was a period of about 300 to 400 years where the glaciers worldwide grew to a greater extent than they had been in over 10,000 years since the end of the Big Ice Age, right? Now, what we initially learned about glaciers and how they grew and how they disappeared and how they melted and so forth was studying the glaciers of the Little Ice Age. Geology was born by these guys like William Buckland and Louis Agassiz that were studying the recession of the ice 150 years ago. And seeing, well, here's the ice coming down here and it's pushed all of this stuff up and now it's receding back and it's left this pile of stuff. They call it moraine, see? So they've been watching and studying the recession and disappearance of the glaciers during the Little Ice Age. Well, extrapolating from that, they then thought, well, okay, now what we have to do is we're going to be looking at glaciers that were much, much more extensive. Now, there's a group out in Washington called the Ice Age Floods Institute, where it's a group of people. I think the first time Brad and I went out there to visit them was in 1998. And we had heard about that there was a group of people who were very interested in some of these big floods. So we went out there and they had they actually met in the Chamber of Commerce. They had a little room in the back of the Chamber of Commerce building in Moses Lake. And I think there was, 2 people there, or 2 elderly ladies. Now it's grown to where there are, a dozen or 15 or 20 chapters. So now there's hundreds of people, and every year they have a couple of field trips guided by geologists, and they go out and they explore this country, and they look at these features and so forth. And on their website, if you go there, they say this: it may be the greatest story yet untold. And I almost agree with that, because I feel that really they haven't even got the full picture yet. And when you get the full picture, it is the greatest story yet untold. No question. See, if something came along in the near future that literally completely erased civilization from this planet and left surviving humanity living a Stone Age existence, having to start all over again from square one and build up over 10,000 years to create a new civilization. And 10,000 years from now, people were looking back into history, you could probably say that whatever the event was that erased modern civilization as we now know it would have been a hell of a story, wouldn't it? Well, see, this, I think, is what we're looking at here. See? And now you have to picture that our models of prehistory emerged within a certain concept of world history, a certain concept of Earth history, rather, and global change, which until the 70s and the 80s was strictly uniformity and gradualistic, right? And so within that framework, you think it's history, and whatever affects human civilization is going to be probably what we would use the term internecine. It's going to be internal conflicts, social degradation, some kind of economic collapse, warfare, various things, but not looking at something outside that could have affected the stability of ancient civilizations. So now, as I've said before, we humans, modern humans, have been on this planet for at least 150 to 180,000 years, right? But we go back only 4 generations ago, and the main mode of human transportation was horseback. So notice that we have had a period of basically uninterrupted forward momentum of science, of industry, of culture, of society. And look at how quickly we went from literally, living where 90% of the human population was living off agricultural-based economy, where subsistence farmers or hunter-gatherers, we're talking only 100 to 150 years ago. When my grandfather was a kid, the main mode of transportation was horseback. There were no cars only 3 generations removed from me. Certainly no airplanes, certainly no rockets, no computers, etc., etc. Now, what I'm getting at here is, if you think about this, if we assume that a generation of human beings, a turnover is, say, 25 years, I think that's a safe number. 25 years from now, there will be all the little babies that are being born today will now be grown up and entering their adult life and having babies themselves, a lot of them. Well, what that means is if we go back to the earliest modern humans, we're going back about at least 7,000 generations ago. Now, these 7,000 generations of modern humans who have just the same size cranial capacity as modern humans, which we assume would be an indication of how intelligent they are. Now, think about this, 7,000 generations. Doesn't it seem like maybe there's some details of the human story on Earth that are missing? Yeah. Now, the question is, why is it missing? And the answer becomes, once we begin to understand how truly dynamic this planet is, right? In the old models, it's gradualistic, it's uniform. So nobody was conceiving that there could be a flood of a billion or more cubic feet per second that essentially would wash away completely 100% of any evidence of human civilization in its path. Now, of course, what I was showing you there was up in Washington State. But I started by showing you something very similar on the whole other side of the continent. So that you can see that actually we could go step by step right across from the Atlantic to the Pacific, and you would be able to see evidence for these gigantic floods emanating off the ice sheet. So what happened was back in the 70s, the early 70s, the glacier scientists and the climate scientists and the geologists and stuff got together, and they started, and physicists, they got together and they had this big conference in 1973. And by that time, radiocarbon dating samples had accumulated. Radiocarbon dating, you know, was invented by Walter Libby in the early 1950s, but it took about 20 years to collect an extensive enough database that one could actually make statistical inferences from that database. Okay, so by the 1970s, it had become apparent that the onset and termination of the Ice Age had come a whole lot quicker than anybody had previously assumed. I mean, a whole lot quicker. So previously they had assumed, well, based on rates of looking at the Little Ice Age and how fast we've seen modern glaciers receding, you know, sometimes 10 feet a year, sometimes 20 feet a year in accelerated cases, sometimes 50 feet a year if the glacier is surging, but that only lasts for a year or two, and then it goes back to sometimes 2 or 3 feet a year, sometimes 10, sometimes 20 feet a year. The glaciers will be receding, right? Well, now they looked and they said, we got this huge, massive glacier that reaches from the Atlantic to the Pacific. And I want to show you basically this slide again so that you can see it. When we come down to the period between 13 and 15,000 years ago, this is what we were basically looking at, right? And if we go back and forth from present situation, there's another version of the two great ice sheets that covered North America, right? Okay, now here's the thing. When we're looking at this, if we start melting this and the margin of the ice sheet starts receding back, just like we saw glaciers doing 150 to 200 years ago, even down to the present day, and the ice is receding back and eventually is gone. Likewise, this receding is gone. Well, they started looking and they said, okay, here's the thing. We know that ice was there fully intact like this 14 or 15,000 years ago, and somewhere between 8 and 10,000 years ago, it's gone. So let's generously allow as much time as we possibly can, and we'll say 7,000 years. Okay, to get from the edges of the ice sheets, and you see this is all the way down like to the Ohio River. I mean, here you've got, this is a climate whose only modern analog is the South Pole of the world, right? The South Pole. This ice mass is bigger than the Antarctic ice mass that now covers the South Pole. And here it is covering half of North America. Right, we're right here. If we travel north and we get up roughly to the Kentucky-Ohio border, we would have been standing right at the edge of this massive ice sheet, right? So now, between 13 and 14,000 years ago, it starts receding back, presumably. This is the model, right? So they look at it and they go, okay, if we allow 7,000 years for this thing to recede back, how much does it have to go each year? And the answer was about 800 feet. Each year, nonstop, 800 feet this year, 800 feet the next year, 800 feet the next year. And they said, well, you know what? That's interesting because it takes energy to convert ice into water. So this is what they did. They said, okay, if we allow this 7,000 years, and it actually has been reduced to more like 5,000 years since the early 70s, they said if we allow, assume 7,000 years, it's going to be roughly 800 feet every year, nonstop for 5,000 years. How much energy does that take to do that, right? So they looked at what's in Canada today, and they realized that the amount of energy that's in Canada today is enough that it does not sustain a giant ice sheet, does it? Every year, northern United States, Canada gets 5, 6, 7 feet of snowfall, right? Spring comes, what's happening right now? It's going to, in the next month, it'll all be melting away, gone, right? So and it's the energy, the sun's heat energy that's causing that snow to melt away and disappear. Well, now we're talking about an ice sheet that might have been 2.5, maybe even 3 miles thick over at the center here, right? Now we got to get rid of that. So how much energy does it take? Well, what they came up with was around 370 kilocalories per square centimeter per year. So where on Earth today do you get that much energy? Nowhere. So they said, well, let's see. Let's look at some places where there's really a hell of a lot of solar energy available. And they said, let's look at African deserts. And they found out that in African deserts, you've maybe got about 150 to 200 kilocalories per square centimeter per year. So only slightly more than half the amount of energy in an African desert. Now, are you beginning to grasp the dimensions of this problem? We have to take as much heat as is now available on an African desert, almost double that, and shine it on this ice sheet for 5,000 years to get rid of it. You see the problem. What they did was they referred to it as the energy paradox. And in 1975, they had another conference to try to get around it and figure out what's going on here. At the end of that other conference, second conference, they said, there's got to be an error in the data somewhere. We don't know what it is. We're going to put this on the shelf and get back to it. Well, here we are in 2015, and guess what? Nobody's really gotten back to it. And you know what? See, part of the problem now is all of the money for climate change research is now going towards anthropogenic climate change, which means what? Humans, right? Do humans cause climate change? Of course we do. Do humans have an influence on climate? Of course we do. Have we increased the amount of CO2 in the atmosphere? I think it's pretty clear we have. Does the amount of CO2 in the atmosphere fluctuate naturally? Yes, it does. Have there been climate perturbations, climate disruptions that go far, far, far beyond anything we've seen in the last 100 or 200 years? Most definitely yes. And this is what I'm trying to introduce you to here now, is that because right now 99.99% of humanity on planet Earth is utterly oblivious to the true dynamic history of this planet, or the true dynamic history of human population and culture and civilization on this planet during the last couple of 100,000 years. Now, what's all this have to do with the Holy Grail? Well, it has everything to do with the Holy Grail. Here's my take on what the Holy Grail is. The Holy Grail is basically an encoding of the technology whereby human beings can accelerate the regeneration of the planet in the aftermath of a catastrophe. That is what I believe the Holy Grail mythos and symbolism is all about. And it goes back, if you heard the first lecture where I talked about that period, the Arthurian period, in the Dark Ages, from about 536 to 540 AD up until roughly the early 900s. What we now see is that there was a minor global catastrophe between 536 and 544 AD. And it caused a significant drop in human population, particularly in Europe. Because what we had was in 536 AD, something happened. The world got cold and dark for decades. This has been recorded in the historical annals of the time repeatedly, repeated references to the sun, the dim sun that could barely be seen, or the sun that was not seen for days at a time, crops dying in the field, people starving, famine. And you know what happens when people are malnourished? They're weak, their immune systems go into decline, right? Then what happens when people have no immunity and no resistance to disease? So it goes. You have famine, you then have pestilence. And this is exactly the model that we see in 536. We see that there's a sudden darkening that comes over the earth that has been documented in a dozen different places. Dendrochronologists, that are scientists that look at tree rings, have been able to see that over the northern hemisphere for nearly a decade, tree growth, forest growth, apparently came to an almost screeching halt for 10 years. Because the tree rings just show suddenly that they're very, very skinny. Like there was virtually no growth at all in the trees of that time, right? So on the one hand, you have historical annals and you have records of, Irish monks talking about how they haven't seen the sun in weeks and how the temperature is cold and it's dark and how crops are dying in the field and people are suffering from malnutrition. And then in 542 AD, we have the Justinian plague. Comes in and wipes out a third the population of Europe. In some cases, in some regions, half to 3/4 of the population was eliminated. So this set back the economic and social and cultural development of Europe by 200 to 300 years. It was that dramatic. And only when the warmth came back into the world in the 900s, and this during the Dark Ages, the sea ice had come down from Greenland, right? Well, it had receded during the medieval warm period, and now you had Scandinavian explorers that could go out and set up colonies on Iceland and even come and colonize as far as the west coast of Greenland. And this was during this medieval warm period, right? And the sea ice retracted way far north. Human population boomed during this period. Why? Because it was warm, there was abundant rainfall, crops, the growing season increased by 4 to 6 weeks over what it had been in the previous centuries. So now there are copious, abundant harvests, people are eating a lot. What we see is population, which first declined and then just held steady for nearly 300 years of the Dark Ages, is now taking off. We see lifespans increasing. We see a decrease in infant mortality. We see an increase in the overall stature of people. The stature of people in Europe over a period of about a century increased by 4 or 5 inches because people were well fed. And now there was surplus crops. They began to trade. There was wealth accumulated. And as an outgrowth of that wealth, they launched this tremendous, awesome period, 150 years of this amazing cathedral building. 200 years earlier, there was not the manpower, there was not the wealth to do it. But now they're building 80 of these tremendous giant monuments that show advanced and sophisticated geometry and engineering and astronomy, symbolism, just rich and replete in symbolism, alchemical and hermetic symbolism that has its origins back in Egypt and Sumeria. And we see all of this going on for about 150 years, right? Then we get to the early 1300s, and what happens? A couple of things happened, both sociologically and climatologically. Sociologically, we had the authoritarian church begin to suppress movements, spiritual and intellectual movements like Catharism and Templarism. Between 1310 and 1314, the Templar organization was destroyed. The Templars were custodians of a very rich, ancient, archaic body of knowledge and wisdom. Okay, and what we see is that almost following right in the heels of the suppression of these alternate groups, the Martinists and the Albigensians and the Cathars and the Templars, what we see is the climate shifted again. And cold came back to the world, and the MWP, the medieval warm period, was over. And literally there are cathedrals where, you know, the architectural historians have looked at it and said, you know what, some of these cathedrals that aren't finished, it's almost as if the workmen just put down their tools and left before the job was finished, right? Well, once you begin to realize how quickly the climate changed from warm to cold, and then you had the same repeat. You had agricultural collapses, you had famine, and then what did you have? Followed immediately by the bubonic plague, which again wipes out a third the population of Europe. And for the next 100 years, everything was stagnant. And then we had about a century of warmth. And then that ended in the Little Ice Age. Second phase of the Little Ice Age came on and lasted until about the mid-19th century, until about 1840, 1850, 1860. We see that the Little Ice Age begins coming to an end. And during this period, picture now the glaciers, which have now disappeared, right? And it's not only just the ice sheets themselves, it's also the mountain glaciers. If you look here, like you see there's huge glacier complexes over the Rocky Mountains, over the Sierra Nevadas, over the Cascades. They all melted back because during the Great Ice Age, those mountain complexes of glaciers were huge compared to what they are now, right? So they were over Europe too, same thing, like the Alps right here were basically buried in a huge ice sheet, right? And in fact, this right here where they first began to study the effects of the Little Ice Age. Now, bear in mind that the Little Ice Age, virtually all the studies suggest that the glaciers during the Little Ice Age, from the 1700s to the mid-1800s, were the biggest they had been in over 10,000 years since the melting of this. This is important to keep in mind when we talk about, you know, modern glacier recession and modern climate change, is that you always have to ask, what's the baseline? What are we comparing it to, right? So we're basically saying our industrial revolution began roughly at the end of the Little Ice Age, see? Now, glacier recession, human introduction of fossil fuel, human introduction of carbon dioxide into the atmosphere really didn't pick up momentum until World War II. Coming out of World War II, what you see is the graph of CO2, human CO2 into the atmosphere looks like this. Slowly rising, then World War II in the 50s, boom, it goes way up, right? But if you look at glacier recession, what you see is that the glaciers are going down at least 100 years before we were putting significant amounts of fossil fuel into the atmosphere. So there was something natural going on here that can't be blamed on humans. So what I'm getting at here is that we've seen, and I'm trying to introduce you to this idea that there are scales of magnitude here in these events. That number one, we're living on a dynamic planet, far more dynamic than anybody had imagined, you know, a generation or two ago. Secondly, there are scales of events, right? In effect, one of the concepts you've got to get in your mind is thresholds, right? Like in the last 10 years, actually the climate has been quite stable, right? Now, if you go back, do you know what the hottest decade of the 20th century was? People are going to typically say, well, it must have been the 90s, right? No, it wasn't. What was the hottest decade of the 20th century? It was the 1930s. Now, in the 1930s, you had agencies that were keeping track of temperatures. And if you look at, on a year-by-year basis, and you look at all 50 states, right, and you go, okay, what was the all-time highest temperature ever recorded in the state of Georgia, or the state of Maine, or California, or New Mexico, or Washington, or Minnesota? What was the highest all-time temperature ever recorded, right? Well, of the 50 states, 25 of them, the all-time highest temperature ever recorded, 25 of them were in the 1930s. What does that tell you? The last time an all-time high state temperature record was set was 1994. And not one record has been broken since then. It's important to keep that in mind because we need to keep this whole climate change discussion in perspective here. Because there is an agenda at work that's primarily concerned with focusing all of our attention on what humans are doing And we, of course, should be paying attention to what we're doing. But there's another factor, and to me, that is the 800-pound gorilla sitting in the corner of the room, is that this. Nobody has an explanation for this yet. Nobody has an explanation for how the world can shift from like it is now into this in a few thousand years, and how it can shift from this back to an interglacial age like we're in now in a few thousand years. Nobody has that explanation yet. Now, given that, should we say that the debate about climate change is over? I don't think so. So I would politely raise my hand if I was, in the audience with Al Gore or whoever who said that the debate is over. And I would say, well, excuse me, sir. There's this little matter of this. And that needs to be part of the discussion here. Well, so let me get back to this idea of the energy paradox. Somewhere there was enough energy to get rid of this ice, not in 50,000 years or 20,000 years, maybe in 5,000 or 6,000 years. Now, the assumption there, of course, is even there in their models that they were coming up with in the early 1970s, they're assuming a smooth rate of continuum, going from the edges here up, getting rid of it all. And here one of the other mysteries is that as the ice recedes, forests and plants start growing, vegetation grows in the lee of the ice sheets, right? So once the ice has been down here, it begins receding back, plants come back, right? So they can come in and they can radiocarbon date when those plants returned to that area. Well, here was one bizarre thing. They saw, okay, well, here at the south end, it receded at this rate, but the north side of the glacier receded apparently at the same rate. So how, for 5,000 or 6,000 or 7,000 years, literally, you're going to turn on something that's half or 3/4 again as much solar energy, heat energy, as available in the Saharan desert, and you're going to turn that on this ice sheet continuously for 5,000 or 6,000 years until the entire mass is gone. Who has an explanation for that? Nobody. Well, with a couple of exceptions. Me. Brad. Graham Hancock. Graham Hancock gets it. He was figuring this out basically at the same time I was figuring this out 20 years ago and realizing, wait a second. It's easy to say, well, if you think that there was this, lost civilization that was able to build a sphinx and do all of this other stuff, well, where is it? We're looking for it. We don't see any potsherds. We don't see any evidence of infrastructure, And that was the claim. Well, we don't see hard evidence of some ancient prehistoric culture, so therefore it didn't exist. But the guys who were saying that were totally oblivious to the real model of Earth change, which is what I'm trying to introduce you to, because it provides, for one thing, it provides a context for understanding the symbolism of the Grail. It does. And that's my whole point here, is that the Grail actually provides an explanation for what happened. Now here's one of my heroes right here, J. Harlan Bretz, University of Chicago, a discoverer of the Missoula flood circa 1923. Through his studies of the channel Scablands of Washington State, his name for the event was the Spokane Flood. Now, basically, it took J. Harlan Bretz a quarter of a century every summer with a team of his students going out crisscrossing southeastern Washington by car and by foot. Took him 25 years to put together and map out what I was able to show you in 30 seconds. That's a pretty significant evolution of our ability to comprehend the world around us. It took him a quarter of a century to create the map of what I showed you in 30 seconds on Google Earth. See, so we're in a really interesting place right now because we have access to more knowledge now, more traditions than basically anybody in, well, maybe 10,000 years, or at least certainly since the destruction of the great libraries of Alexandria and Carthage. But even then, they had all those tremendous manuscripts there in those those libraries, but they certainly didn't have Google Earth. They didn't have satellite photography where you could, because when I showed you these channeled Scablands, Let's look at them. Here's a nice color version of the two great Scabland tracks. The Telford, as it's called, the Cheney Palouse, as it's called. Well, this is taken from 500 miles up. Actually, I think this goes back to the late 70s, 78 maybe, when this was taken. Does that sound right, Brad?
I think it was earlier than that.
Maybe even earlier than that, right. Okay, well, you can see that with the advent of satellites now, we're getting this new perspective. And this is what I'm saying. It took J. Harlan Bretz a quarter of a century to map this. His maps are remarkably consistent with the satellite photographs. But again, it took him 25 years to do that. And we can look at this in an instant. We can see, here's the imprint of something really interesting on the landscape. It's huge water flows. You know, how much water flow? Well, hundreds of millions of cubic feet per second to create these landscapes. And I'm going to show you some pictures of those landscapes so you can begin to appreciate. This is in Montana. I think I showed you this, didn't I? How many of you have seen this one? Okay, good. Then I haven't showed. This is Mount Jumbo outside of Missoula, Montana. And do you see the horizontal lines? Those are shorelines. Geologists call them strand lines. Same thing though, they're shorelines. In other words, the water was up here at one point. For a short period of time, the water was up there. And then it drained away. Didn't drain away completely smoothly. It pulses, right? It's draining away, and each time it pauses, it leaves a shoreline. Now, basically, where Missoula, Montana now was under temporarily impounded body of water almost 1,000 feet deep. Now, this is over in Montana, right? Now, the Scablands that I showed you, that's Washington. Remember, and the Finger Lakes was New York State. Well, we could just keep going. You know, in fact, I could begin to show you hundreds of things like this. So you essentially realize that the North American continent was basically submerged, was literally drowned, if you will, at the end of the last ice age. Of course, what we're seeing here is not limited by any means to the North American continent. That's an important thing to grasp as well. Here's an older photograph taken in the winter where you can really clearly see shorelines. Okay, now this is an event that happened, it left its imprint in the landscape, and now it's gone, it's over with. People are living here. And for years people referred to these as buffalo trails. They didn't know what they were. Of course, buffaloes aren't going to go in nice parallel echelons like that, unless they're very well-trained buffaloes.
It looks like terraced farming.
It does look like terrace farming, but the terraces are much more subtle. I mean, as you see here, when we go back one, you'll see that they're...
So would each of those striations be like a season, a year, or?
No, I would think that each of those, you have to bear in mind, and I'll show you the larger scale map of this, but you know, if you have a basin, let's say a nice round basin full of water, and you have one outlet, right, and you open that outlet, it's going to pretty much drain out uniformly. But let's say that there's a pipe connecting this basin to another basin, and then that pipe in some places is fat, in some places it's skinny, it's constricted, some places there's bends, then it goes into another basin, and then that's connected by a series of pipes or channels to another basin. Well, okay, now let's take the uppermost basin that's filled with water and we're going to drain it, but instead of just draining out one hole, it's got to go through all this whole maze of things, right? Well, what you're going to see is that the draining of that basin is not necessarily going to be smoothed down, particularly if there's stuff in the water. Now, I grew up in Minnesota, and one of the very favorite things that we used to do as kids was about this time of year to go out to some of the local rivers. Mississippi River was a good one, and watch the ice break up, right? And it would be really quite a thrilling experience, because if you got out there the right day, it would almost sound like explosions sometimes when you'd hear these enormous cracks in the ice. And then the ice begins to buckle, right? And the water pressure is coming down because, for one thing, because of all the snow melting, the river's swollen, so there's more water than there would be, say, in the late summer. Okay, now the water's coming down. You've got all this broken up ice. And let's say you got a bend in the river. Well, what happens is the ice, you get an ice jam, just like a log jam, right? You get an ice jam, or the channel constricts, or there's a bridge there. And sometimes if it got really backed up, an ice jam behind a bridge, they would go in there with dynamite to blow up some of it to break the ice jam so the stuff could flow down. Well, now you picture you've got that ice jam, so let's say that the channel constricts. So what's happening is all the broken ice is trying to get in there. It gets stuck temporarily. What happens upstream? The water begins to rise, doesn't it? What happens is the water begins to rise, the pressure increases. And at some point, it'll push it through. And when it pushes it through, the water drops, doesn't it? Now, here what you had was water that was impounding in a basin in western Montana that was ultimately headed to the Pacific Ocean. But in order to get there, it had to go through the same thing I'm describing. Sinuous channels where there's constrictions, where there's basins, and just like the ice of the Mississippi River, this water is choked with icebergs because those icebergs were the byproduct of the great ice sheets disintegrating, you see? So it wasn't just meltwater pouring off the ice sheets. The water coming off those ice sheets was choked with armadas of thousands and thousands and thousands of icebergs. Now, all that is going to be conveyed from here, 500, 600 miles down the Pacific Ocean. All the way along, there's going to be obstacles. There's going to be bends in the river. There's going to be constrictions. There's going to be all of these things that's going to cause what a hydrologist would call a pulsating hydrograph. In other words, the water level will be rising downstream somewhere here. It'll force it through, and then the water level will drop. And that's what you're seeing here. So what may be separating these is more like probably a matter of a few days rather than a few years. A few days. Because the whole process that we're looking at here might have been a few weeks to a few months in duration. From the time of the initial catastrophic melting until all that water had managed to drain and convey itself to the Pacific Ocean out here. Finger Lakes, it's headed to the Atlantic Ocean, but out here it's headed to the Pacific Ocean. And see, here's the thing. What I'm presenting to you is a new model of the world, so that hopefully, if you get enough inspired and you start looking into some of this kind of stuff, you begin to understand that the whole world is the repository of this tremendous story. And it's everywhere about us, but it's on such a grand scale that almost no one yet recognizes it. Go back to the 1920s, you had one man on the planet, J. Harlan Bretz. He was like the first guy for whom he had that awakening, that understanding that this thing happened. And he was totally marginalized and pushed to the fringe by the geological mainstream. And it took him, like I said, a quarter century of doggedly gathering the evidence together until he could build a case and answer every objection of every critic. And finally, he began to sway people to his point of view. But really it was more a case of a lot of the older critics died off, and you had younger geologists that came along that were a little bit more open-minded and willing to actually go out in the field with him. Like a lot of his most vociferous critics wouldn't even go out and look at it. There is one story, though, of James Coulee, though, who actually led one of the attempts to suppress this catastrophist heresy, or this diluvial heresy of Bretz. So they invited him in the 30s, I think it was, to Washington, D.C. to give a presentation of his evidence and his findings. But what it really was is the whole gang of uniformitarian-minded geologists were going to gang up on him, and basically their strategy was, or their motive was, to obliterate this heresy of this gigantic flood. And the guy who led that was named James Coulee, the guy who organized that, right? He was one of Bretz's main critics. Well, finally, as the tide began to turn, he reluctantly went out on a field trip, and this was probably now the early 50s, if my dates remember right. They spent a week out in the field, traveling over this landscape. looking at one feature after another, looking at these giant eroded potholes, looking at these massive boulders sitting out in the middle of nowhere that were not dropped there by ice because it was 50 or 100 miles south of where the ice border was. These giant abandoned cataracts with little trickles of waterfall over them that were just 1,000th or less part of, the volume of water. So they had spent a week out there. They were at a place called Horseshoe Falls, which I'm going to show you a picture of. And it said that after this week, Coulee, the last few days of the expedition, he wasn't saying much. And then the last day of the expedition, where that place called Horseshoe Falls, said he walked off by himself and was standing there looking at this big round basin, which I'm going to show you a picture of, in this huge cataract with this tiny little waterfall coming over it, and stood there in silence for a long period of time, walked back up to the group, shaking his head, and said, "How could I have been so wrong?"
Whoa.
Now that was, that to me, okay, true scientist right there. True scientist. Which we need more of. Problem is now there's so much money in science that, these guys are going, well, let's see, if I come out and say what I really think, yeah. So for example, we look at this, right? And what you have is some beautiful mountains. You have this big flat area, see? Well, it's flat because it was the bottom of this giant temporary lake, right? When this flood came, this whole valley filled with water 1,000 feet deep. And when it drained away, it left a nice flat valley floor, see? Now, you've got farms and ranches out here and tourists driving over. Here's the highway. I guarantee you, 99.999% of the people who traverse this landscape have no clue of the story that's encoded in this landscape. Here, in fact, that basin, that picture, see this highway right here? That was the highway in the picture. And here's the mountain range, the Mission Mountains that we're looking at. This whole thing was filled with water 1,000 feet deep. And the arrows that I've shown here show the points of discharge where that water drained out to ultimately head towards the Pacific Ocean.
Is this still Missoula?
No, actually Missoula's down here. Some of this water did end up in Missoula Basin. Some of it did, yes. Why, have you been to Missoula?
I have, yeah.
Oh, okay. Did you remember the shorelines?
No, I think I saw that, and I thought it was like terraced farming, because that's what it looked like to me.
Yeah.
Yeah.
So, but you see, you noticed it. That's good.
I noticed.
And now if you ever go back again, this time you're going to see that it's something else. It's natural.
I'll look at it with different eyes.
You will look at it with different eyes, yes. Now, there's one place right here that's very interesting in what's called Camas Prairie Basin. Right here, you can, these mottled hills, this moraine, this is terminal moraine. There was an ice lobe that came down right here, and this is terminal moraine called the Polson Moraine. The little town of Polson is right there and gives its name to the moraine. There was a gigantic meltwater gush that came off of this area of the ice sheet, right? While all of this over here, Cheney, Palouse, Scabland, Telford, Scabland, Grand Coulee, Moses Coulee, all that's going on over here. Here, we have these huge gushes of water coming down this way. There was, really the best way to visualize this is almost like the onset of a tsunami. Coming down here, and it hit this range of hills and poured over these hills and pulled millions of tons of sediment out into this basin, Camas Prairie Basin. Right here below those hills is one of the really most profoundest clues as to what happened here. Here's a closer up view of Camas Prairie Basin. Here's that range of hills. Here is a mountain valley that served as a temporary outlet, but this mountain valley is about 500 feet above this floor here. So what happened was the water poured through here. It was so turbulent. See, the water now that's turbulent tends to pluck and scour and deepen the bedrock. And oftentimes, once the water has passed, it will leave these over-deepened scour holes filled with water, right? And now they're lakes. That's what this is. Beautiful, pristine, serene-looking lake, totally inconsistent with the amount of energy and violence that created it, though. as the water continued to drain away, it flowed out here to the south, and this mountain pass was left high and stranded. So if I go to the next view, I'm showing the arrows show the routes into the basin and the routes out. But what we're interested in is the floor of the basin. Before we get to that, I want to jump back and show you current rippled sand deposit on the floodplain of South Fork Peachtree Creek after Hurricane Ivan flooding. The floodplain is now occupied by Medlock Park. It had been decades since any flood had overtopped the modern banks of the creek. If we look at the close-up view, this water, I was able to measure it because, let's see, on the adjacent buildings, you could see the high water mark. It left a trace 23, almost 2 feet off the flat surface of the ground, right? When that water drained away, it left these current ripples, just like you'd see typically at any beach or any sandbar along a creek. And I put a measuring tape here. You can see wavelength 2 to 3 inches, amplitude 3/4 of an inch to an inch, right? Okay, so now what we're
This is
going to...
at Fort Peachtree Creek?
What?
That was at Fort Peachtree Creek?
This was at Peachtree Creek.
But at the
Yes.
fort, the little fort there?
This was down, no, this was down by Medlock Park area in Decatur, near DeKalb Mall, actually. There's a little place down there called, well, no, there's Medlock Park. And in 2004, with Hurricane Ivan, the whole park got flooded. And when the water drained away, it left all the baseball diamonds and the roadways and everything covered with this rippled sand. See? So I was able to go down there and look at the amplitude and scale of these ripples, and also to see right on the buildings, you could see exactly how high the water had become, see? Okay, so then when we start looking at these passes on the south side of these hills, what do we see? Here's the range of hills. Look at this. The whole floor of Camas Prairie is rippled with giant current ripples. Let's see, let's find a good one here where you can really see what's going on.
Randall, exactly where is this?
This is in western Montana. This was one of the spillways where the water came through. And basically when you start seeing this eroded rock with this really rough texture on it, slow erosion likes to smooth things off. It rounds off sharp corners, smooths things off. It lowers the high places, fills in the low places, right? Catastrophic erosion, on the other hand, plucks and quarries and breaks and fractures, you see. Can you begin to see the ripples in the landscape? Those are giant current ripples. This is taken from an airplane. I think we were, a couple of thousand feet up when we took this. You can see the whole floor is mantled. And in some cases, the high ones, 30 to 50 feet. Wavelength, 200 to 300 feet. Now see, right there is unambiguous evidence of gigantic. There is no other way to explain this, you see. Now, I'm showing you little bits of this, but we could go, and it's not my point to give you this detailed from the Atlantic to the Pacific. But what I'm showing you is snapshots of areas along the way. And my point is that this stuff is all around us, and it's on such a scale that we don't really even see it. Until, like here, like I said, this is 2,000 feet up in the air. You can see here's a ranch down here, you see. There's another one there. I mean, this is what my point was, the rapid growth of the Ice Age Floods Institute is mostly local people out there that have, within the last 10 to 20 years, have started to become aware of the fact that they're living on top of this awesome story, you know. Of course, the Native Americans knew this all along. And all of their myths and everything, they basically give tremendously interesting details about these events. So as you can see here, the water came from left to right, and this is a big fan that you find this at the mouths of rivers in modern times. After any flood, you can see there will be a fan. If you go down by any little creek, with a tributary, oftentimes you'll see these little fans splayed out. That's what this is. This is a delta type fan, and then there's ripples on top of that, and you can see all of the ripples in here. So those ripples are, like I said, unambiguous evidence that there was something really extraordinary that happened here. Here's another one of these little scour hole lakes that I was talking about. You see, this was one of the spillways, and you've got the whole thing. Here's the delta fan that we just saw. It's got the ripples. Here is the tortured rock that's got this really rough texture. Here's a scour hole, because in turbulent water, there's all of this. You know, there's all this kind of swift eddy stuff like this that can just pluck and gouge, just excavate right into the bedrock. Then when it's gone, it leaves a residual ponding behind. This may be spring fed, I don't know, but there's a lake there, and that's exactly what it is. So see, once you begin to learn this language, each one of these is like in part of the alphabet. You see, you look at the ripples, you look at the cataracts, you look at the strand lines, you look at the scoured holes, and you begin to put all of these pieces together, and it's a language. And you can then begin to read the story that's been etched into the surface of the earth and waited 10 or 12,000 years until we humans had evolved the intellect and the perspective capacity to see it. So that's what I'm trying to show you, is that yes, these things have happened, and they've gone unappreciated for 10,000 years because we didn't have the sophisticated perspective that we now have that allows us to know that this is here. You are now, I'm hoping, becoming aware of the fact that catastrophism is a major part of Earth history. So, we have to now try to put ourselves in the shoes of those who lived pre-catastrophe and post-catastrophe, right? Now, I've shown you a little bit of this, just a few little pieces of I mean, I could literally show you thousands of slides of these features, because that's how extensive and how ubiquitous it is, right? But now we have to place, what we're ultimately trying to do is place the human story within this context. See? So now you picture something like this is coming on, and what I'm showing you here, I'm showing you regional effects, but those are the regional expressions of a global event. Let's be clear on that, right? Pacific Northwest of North America preserves some of these features in a very spectacular fashion, and that's why I find it always very useful to begin showing that first. Start with the really spectacular stuff, and then as you begin to develop a sense of the language and the syntax of it, you can then go and begin to appreciate the more subtle effects. The effects, for example, that we can find by a 1 to 2 or 3 hour drive from where we're sitting right now. But actually some of those are not as subtle as you would think, and I'm going to show you some of that. But here's the thing. In the aftermath of something like this, you have to see that what this is an expression of a short-lived, massive, intense destabilization of the natural order of things. See, and the reason I'm going into detail and aim is I want you to really grasp this, because this is the context in which I'm trying to place the Holy Grail stories. Because the Holy Grail stories, like I said, were written down between 1180 and 1230 AD. But they refer to a time that goes back to the days of Arthur and Camelot and the quest, right? Which was set in the late 530s and early 540s. And we now know that something happened. Now, what happened then? Not near the severity of what happened here. But it was severe enough that it interrupted the forward momentum of Western civilization for at least a couple of centuries. And were an event like that magnitude to happen again, it would seriously, seriously stress modern civilization. We would probably weather it, but only at tremendous cost. I mean, can you imagine what would happen if we had 3 years of agricultural collapses in a row? That would be pretty intense. And there would be a lot of mortality associated with that. What I'm getting at here is in the Grail, I think we are looking at a technology, and I use that term, maybe a spiritual technology, but a technology whereby the process of recovery to natural stability can be accelerated. And if you were paying attention the very first lecture and putting together what I was saying then, by actually getting in, reading some of the Grail romances as they're called, that was the point that I was really trying to introduce at the very outset here. Because you see, remember in the story of the Grail, what happened? The king, whether his name was Arthur or Bronn or Anfortas or the Fisher King, it was the same deal. He was disabled somehow. He was sick, he was infirm, he was disabled, he had a wound that wouldn't heal. And at the same time, the land around was suffering from blight. People were sick and starving, cold and dark. And this is what the wasteland, this wasteland concept that has come down to us through the Grail literature, we now know was literally true. It literally happened. Right? Now, whether it was Galahad or Lancelot, not Lancelot, but Percival, who went out ultimately questing for the Grail, if he succeeded in finding the Grail, the two things that would happen simultaneous were what?
The king would heal.
The king would
And the
heal,
land.
and the land would heal. Yes, exactly. To me, I'm looking at that, well, this maybe this is more than just metaphorical. Maybe we're really looking at something here whereby when there has been a decimating effect, natural effect, maybe there's something that people can do to help restore and bring back the vigor and the fertility to the land quickly. And you know what alchemy, in alchemy, what they're doing, if you read the philosophy behind alchemy, which has so many parallels with the Grail mythos, if you read the commentaries on the alchemists, what are they saying? Well, they're saying all we're doing is we're mimicking nature, but through our alchemical procedures, we're simply accelerating what would take place naturally anyway. Well, I'm submitting to you the idea that perhaps this is what the Grail was all about. The cleanest, simplest representation of the Grail was the chalice cup. But as we've learned, there were multiple imagery. There was a complex imagery associated with the Grail. We're going to come back to this because one of the parts of what I want you to take away from this series of lectures is a deeper understanding of the story that's been preserved in the landscape for 10 or 12,000 years. Because right now I feel like it's critically important that we humans come to terms with that and begin to understand this language of catastrophism, if you will, and this story that it represents. Because right now I feel like it's critically important that we humans come to terms with that and begin to understand this language of catastrophism, if you will, and this story that it represents that's etched and preserved in the landscape. Once we've got that, we can have a context for understanding all kinds of other things, not just the Grail, but, when we turn to religious and spiritual traditions from all over the world, and we find that from the Middle East to the Near East to Celtic Europe to Egypt to South America to the North American native indigenous tribes to China to India to Siberia, Eskimos up in Alaska, all have preserved tales of a gigantic world-destroying flood, right? Well, the fact that so many cultures have preserved some form of this story, to me, is just awesomely important and significant. And it tells me that, well, that is probably something that we should come to terms with, because we're in a place now where a couple of generations ago, you had religious people who believed on faith and didn't need an explanation because, it's all supernatural. God can work miracles, so this is evidence for the flood of Noah and we don't need an explanation. Scientists were saying, and when they leveled their criticisms at J. Harlan Bretz, they said, well, you're trying to bring back the biblical flood. Get out of here. We did away with that 100 years ago and now you're trying to bring it back again, right? So you had these two antagonistic camps. One, religious perspective of the world, the other is the scientific world, and never the twain should meet. But now we're in a position really of a higher perspective on this, where we can see that what these traditions were that we've inherited from the past, whether it was the Grail tradition from 800 years ago or mythical traditions going back 4,000 and 5,000 years ago to Egypt or Sumeria or in the Indus Valley or other places, that those are actually scientific information encoded in this imagery that has been transmitted for generation after generation after generation in the form of these tales, these epic tales, the poetry, the myths and so forth, oftentimes being perpetuated by people who themselves really didn't even have a clue as to what the meaning was, the reality behind these stories, see? But now we're in this unique and privileged position where we can say, yeah, there is a reality behind these stories of the flood. There's something very real that did happen, and it wasn't supernatural. Well, not in the sense that we think of something miraculous, but we can actually now begin to understand it scientifically. Maybe it is supernatural in the sense of supernature, because ultimately what we're seeing here, and this is the thing I want you to really begin to integrate, because this is just intrinsic to the whole Grail concept, is that what we're seeing here is the imprint of cosmic phenomena. And we have to begin to understand that the Earth has not evolved in a cosmic vacuum, but is part of a larger cosmic ecosystem. And we have to begin to transform our thinking from purely ground-based, terrestrial-based, and understand that our planet is part of a much larger cosmic environment, and what goes on in that cosmic environment has a lot more effect and influence on things down here below than we had imagined recently. But not so with our ancestors, because they knew. That's why they were such obsessive sky watchers. That's why everywhere we go, no matter where, whether it was megalithic Britain, whether it was the temples of Egypt along the Nile, whether it was the Sumerian ziggurats, whether it was the monumental earthwork of North America, whether it was the limestone structures of Mesoamerica, whether it was the Incan stuff, whether it was the architecture of Cambodia and Thailand, in every single case, we find this consistency, which is that it's oriented towards the cosmic realm, oriented towards the astronomical realm. And it's marking all of the celestial motions and patterns, the tempo of cosmic change. And that's what these are. They're instruments for observing and monitoring cosmic change, the tempo of cosmic change. Why would they do this? I mean, going back to Norman Lockyer at the beginning of the 20th century, he was the guy who went out and looked at Stonehenge and said, you know what, this is an astronomical observatory. And everybody said, get out of here. You're a really smart guy, and, you know, we all recognize that you're a really smart, you know, preeminent archaeologist, but hey, get out of here. Those people weren't astronomers back then. They were just barbarians and holding human sacrifice. Well, of course, he was right. And now we see, you know, Graham Hancock has been involved in the excavations of Gunung Padang and Göbekli Tepe, and there's some really, really intense stuff coming out of Göbekli Tepe. And when Graham's new book comes out, he's going to have a lot of detail in there. But it appears that Göbekli Tepe was built just prior to this event that we're seeing here. Now, one of the mysteries of Göbekli Tepe and why it's now just being uncovered is that it was deliberately buried. It was deliberately buried. And it's a huge, vast complex of stones, and already they've uncovered enough of it to see that the whole thing is an astronomical observatory. Just like all these other structures all over the ancient world were astronomical observatories, right? Which is one of the critical facts that has to be incorporated into this thinking about the Holy Grail technology, because the Holy Grail technology actually is linking these two domains, terrestrial, celestial. And without looking from that dual perspective, we would not be able to understand what the symbolism of the Grail is actually communicating to us. But in Göbekli Tepe, it was deliberately buried. In our road trip that Brad and I took with Graham last October, because we showed Graham all of this stuff. We took him from almost the Pacific Ocean over to the Midwest, to Minneapolis. And we basically followed the route of the southern margin of the ice sheet so he could see for himself the scale of this stuff, because he knew that there had been a catastrophe of some level of magnitude. He wrote about it in Fingerprints of the Gods back in 1995. And he speculated that there was a celestial component to it, but didn't go into great detail on it. Brad and I have made, a dozen trips out here and crisscrossed this whole area. We took Graham along here so that he could see this himself, and there's going to be a large part of this, at least 4 chapters in his new book, Magicians of the Gods, is going to be devoted to what we discovered on that trip. But now he went from there to South Africa, and then he went from there back to Turkey, back to Göbekli Tepe, if memory serves me correctly. And anyways, we had extensive discussions about how Göbekli Tepe was buried, and I was just thinking about it and thinking about it and thinking about it. And the reference that I think, and of course I can't prove this at this point, but I have a strong intuitive hunch that the reason that it was buried was the very same reason that you bury a missile silo, for example.